Hey guys, today we're going to learn how to find limits of trigonometric functions. Now, in order to find limits of trigonometric functions, we need to be familiar with how to use the unit circle. Remember that in calculus, we're not going to be using degrees, so we can ignore all of the degree measures, so we can only focus on the radian measures. Now, this is quadrants 1, 2, 3, and 4. In order to find the limits of trigonometric functions, we need to know the unit circle, how it works, how to read it, and additionally, we need to have these coordinates here memorized. Now, as long as you know quadrant 1, you don't need to know the rest of the unit circle because the quadrants will tell us exactly what is positive in each quadrant, like what trig function is positive, and then the coordinates for each of these radians are always the same. The only thing that changes are the signs. So this is how it works. For the radian measures, we have the denominators 6, 4, and 3. In any quadrant, wherever you go, the coordinates will remain the same for all of the radian measures that have a denominator of 6. So if we notice cosine and sine, we have square root of 3 over 2, comma, 1/2. So the cosine of pi over 6 is the square root of 3 over 2, and the sine of pi over 6 is 1/2. So just as a reminder, right, this is because the x is the cosine of the angle, and the y is the sine of the angle. As long as you know cosine and sine, you can figure out any of the other trigonometric functions, since the rest of them all have to do with cosine and sine. Now, let's review these angles a second. If you're in quadrant 1, the angles is always just pi over whatever the denominator is. In quadrant 2, the numerator is 1 less than the denominator, so that's why it's 2 pi over 3, 3 pi over 4, 5 pi over 6. In quadrant 3, the numerator is 1 larger than the denominator. And in quadrant 4, the numerator is double the denominator minus 1. Now for the signs, if you remember, all students take calculus. The A stands for all trig functions are positive. The S means that sine and its reciprocal cosecant are positive. T for tangent and its reciprocal cotangent are positive, and C, cosine, and its reciprocal secant are positive. So let's say if I ask for the sine of 11 pi over 6. 11 pi over 6 would be in quadrant 4, since the numerator is double the denominator minus 1. And in quadrant 4, only cosine and secant are positive. So that means that the sine of 11 pi over 6, I'm just going to write it out so we know what problem I'm talking about, would be negative. Now, as long as you know that quadrant 1, the sine of pi over 6 is 1/2, then the sine of 11 pi over 6 would be negative 1/2. So the number never changes, only the sign changes. So that's why we remember this and just quadrant 1. Now you'll also have to remember the quadrantal angles, which are the angles that lie on an axis. A full revolution is 2 pi. So if you divide 2 pi by 4, because there's 4 axes, then we get 2 pi over 4, which is pi over 2. So that gives us the first quadrantal angle. At another pi over 2, you get 2 pi over 2, which is pi. At another pi over 2, we get 3 pi over 2. And at another pi over 2, we get 4 pi over 2, or 2 pi, which gives us back to the beginning. Remember that this is the unit circle. That means that the radius is 1 unit, the unit. So as long as you can remember that the radius is 1, if you're on the positive x-axis, the coordinate would be 1, 0. If you're on the y-axis, then that means that the radius, which is 1, would lie on the y, so the coordinate is 0, 1. If you end up at pi, this is away from the origin on the left, so the coordinate would be negative 1, 0. And if we're at the negative y-axis, then it would be 0, negative 1. So that's how you can figure out those quadrantal angles. Now I just want to go over a neat little trick on remembering these coordinates. As long as you remember quadrant 1, this is pi over 6, pi over 4, pi over 3. So just remember 6, 4, 3. Or if you want to write it going down, the numbers increase as you go down. So 3, 4, 6. Now for the coordinates. If you look at all of the coordinates here, all of the coordinates are over 2. So we can set up our coordinates here as all over 2. Now remembering the numerators. If you start on the very left side, and everything in the numerator, we're just going to put square roots. Now you just put 1, 2, 3, and then go write 1, 2, 3, but now going back up. 1, 2, 3. Then what we can do here is that since the square root of 1 is 1, we can erase this radical here and this radical here. And this gives me the coordinates for quadrant 1. So it's a neat little way of remembering these quadrant 1 coordinates. So 6, 4, 3, or if you want to go down, 3, 4, 6. Everything is over 2. Put square roots in all the numerators. Then 1, 2, 3, 1, 2, 3. You've got quadrant 1 done. If you are working on your assignments, I always recommend just drawing out quadrant 1 in all of your assignments that have any trig on it. The more you write it, the more you'll remember it, and eventually you won't need to draw it out anymore. Then the quadrantal angles, you just have to remember that the radius is 1 to help you determine what those coordinates are. Now let's get into the heart of the lesson, which is evaluating these trigonometric limits. Let's start with this first one. We have the limit as theta is approaching 2 pi over 3 for sine of 3 theta over 3 theta. So far when we've done limits that involve trigonometry, all we've done is we've taken the angle and we've plugged it in. So that's what we're going to do here. We're just going to check to see if that we remember how to do this. So here I'm going to plug in the 2 pi over 3 everywhere I see a theta. So sine of 3 times theta, which is 2 pi over 3, all over 3 times 2 pi over 3. The 3's here would end up canceling, and here as well. So we have now the sine of 2 pi all over 2 pi. The sine of 2 pi, this is on the positive x-axis. So this is the coordinate 1, 0. The sine is the y value, so the sine of 2 pi is 0, divided by 2 pi. 0 divided by anything would give me an answer of 0. Now let's do the limit as theta approaches pi of 2 cosine squared theta. Now just so you understand what this says, when you have your trig function squared followed by the angle, this means cosine theta, once you find this value, it is squared. This is not the same as this. This means that only the angle is squared, whereas this one means that the entire trig function is squared. So let's work this out. We're going to plug in the pi. So this would be 2 cosine of pi, and then we're going to square it. Now pi, that's over here on this end. This is the coordinate -1, 0. So the cosine is -1. So this is saying 2 times -1 squared. -1 squared is 1. So my answer is 2 times 1, which is 2. Now let's look at this last one here. We have the limit as theta approaches 0 of 1 minus cosine theta over sine squared theta. So we're going to plug in the 0. 1 minus cosine of 0 over sine of 0 squared. Now 0 is the same spot as 2 pi, which is 1, 0. So this will be 1 minus the cosine of 0, which is 1, over the sine of 0, which is 0 squared. This gives me 0 over 0. Now we learned if we have 0 divided by 0, this is not necessarily undefined. This is called indeterminate. Now this is indeterminate because what this means is that there is possibly a limit. But what's going on here is that there is a hole. And if there's a hole, that must mean that I can take this function to rewrite it and then be able to cancel out a common factor so that I could find that limit. So let's see what we can do here in order to evaluate for this particular limit. Now the trick here is using our identities. These are the most commonly used identities, which are the Pythagorean identities. It's because they kind of look like the Pythagorean theorem. A squared plus b squared is equal to c squared. Which if you look at this, all of these here have to do with squared. Sine squared theta plus cosine squared theta is equal to 1. 1 plus tangent squared theta is equal to secant squared. And 1 plus cotangent squared theta is equal to cosecant squared theta. So anytime you see a trig function that's being squared and you can't evaluate the limit, see if you can apply a Pythagorean identity. This is the previous example we just tried finding the limit for, and we noticed that it didn't work. Sine squared theta, however, I could rewrite this by using a Pythagorean identity. The only Pythagorean identity that uses sine squared is this first one. If I take this identity and I solve for sine squared, because that's what this is here, I would subtract cosine squared to both sides, and I get that sine squared theta is equal to 1 minus cosine squared theta. So that's what I'm going to do. I'm going to take this sine squared and I'm going to substitute it with this. So let's rewrite this limit. This is going to equal to 1 minus cosine theta over 1 minus cosine squared theta. Now 1 minus cosine squared may be difficult to see, but this is a difference of squares. 1 because it's a difference, there's subtraction. 1 is a perfect square because the square root of 1 is 1. And cosine squared is a perfect square because if you square root cosine squared, it would cancel out the exponent and leave me with cosine theta. So I can rewrite this denominator. This is going to be 1 minus cosine theta over 1 plus cosine theta times 1 minus cosine theta. And I got that by applying my properties of a difference of squares. So now what happens is that the 1 minus cosine theta will cancel. So this is my limit now. The limit as theta approaches 0, since everything canceled in the numerator, this would be 1 over 1 plus cosine theta. Now I can plug in the 0. This is going to equal to 1 over 1 plus the cosine of 0. The cosine of 0, again, if we think about our unit circle, is 1. So this is going to equal to 1 over 1 plus 1, which is 1 over 2. Let's try this other one here. Here we have the limit as theta approaches pi over 2 of 3 cosine squared theta over 2 minus 2 sine theta. Now pi over 2, if I were to try substitution and plug it in, I would get 2 minus 2 times the sine of pi over 2. The sine of pi over 2 is 1, so we would end up with 2 minus 2, which is 0. So this is where I would have to try to rewrite this trigonometric function so that I can find this limit. Let's see what we can do. Here in the numerator, I have cosine squared. So I'm going to use my Pythagorean identity. I'm going to switch colors here because this is just using the identity, which is sine squared theta plus cosine squared theta is equal to 1. I want to substitute cosine squared theta with the appropriate identity. So I'm going to solve for cosine squared theta here. So I'm going to subtract the sine squared to both sides. This will give me that cosine squared is equal to 1 minus sine squared theta. So I'm going to replace that with this right here. So this is what we would get. 3 times 1 minus sine squared theta all over. Now let's look at the denominator. Both of these terms have a 2 in common. So I can take out a 2. And that would leave me with 1 minus sine theta. Now, just like in the previous example where we saw 1 minus cosine squared is a difference of squares, so is 1 minus sine squared a difference of squares. So this can be factored as 3 times 1 plus sine theta, 1 minus sine theta, all over 2 times 1 minus sine theta. These factors here would cancel. So here's my new limit. The limit as theta approaches pi over 2 of 3 times 1 plus sine theta all over 2. Now let's plug in the pi over 2. So 3 times 1 plus sine of pi over 2 all over 2. Again, looking at our unit circle, we have 3, 1 plus the sine of pi over 2, that's up here. That's the coordinate 0, 1. So the sine is 1 all over 2. This is 3 times 2, which is 6, and 6 divided by 2 is 3. Let's look at some other identities that are commonly used for these types of limits. These are the reciprocal functions that we've used already in the past. We have cosecant, which is the reciprocal of sine and can be written as 1 over sine x. We have secant, which is the reciprocal of cosine, that could be written as 1 over cosine x. And then we have cotangent, which can be written as 1 over tangent, or cosine over sine, since tangent is sine over cosine. And since they're reciprocals, that just means that this fraction gets flipped to give us this one. So here we have the limit as theta approaches pi of sine of theta over tangent of theta. If you were to try to find the tangent of pi, right, by plugging in the pi, we would end up with 0 in the denominator. So let's see if we can rewrite this so that I can find this limit. One of the easier ways of working through these, especially if you don't have any exponents, is to rewrite your trig functions using only sine and cosine. So let's try that out. The numerator is already using sine, so we're going to leave that. But tangent can be rewritten as sine of theta over cosine theta. Now this is kind of like dividing fractions. Even though sine of theta is not a fraction, we can easily put this over 1. So we have sine of theta over 1. And remember, when you're dividing fractions, you're multiplying by the reciprocal, or change to multiplication, and then flip. See, now here we notice the sine will end up canceling. And I'm left with cosine theta over 1, which is just cosine theta. So now let's try to find this limit. This is the limit as theta is approaching pi of cosine theta. Now we can plug in the pi. The cosine of pi, that's over here. This is the coordinate -1, 0. The cosine is -1. So this is going to equal to -1. Now let's try doing a couple of examples. We have here the limit as theta approaches 3 pi over 2 of tangent theta cosine theta. So let's see if we can rewrite this using only sine and cosine and then see what happens. Tangent is sine divided by cosine. And then we're going to multiply by cosine. See, now what happens here is the cosines cancel. So now my limit is the limit as theta approaches 3 pi over 2 of sine of theta. Now we can plug in the 3 pi over 2. So this is the sine of 3 pi over 2, which 3 pi over 2 is down here, which gives me the coordinate 0, -1. So this answer is -1. Let's look at this one here. We have the limit of as theta approaches pi of cosine theta tangent theta over sine of theta. So I'm going to rewrite everything using only cosine and sine. In the numerator, we have cosine theta, and then tangent theta is sine theta over cosine theta. And all of this is over sine theta. So now what happens here is the cosines cancel. And in the numerator, I'm left with sine of theta over sine of theta. Sine divided by sine, that's 1. So this is my limit. The limit as theta approaches pi of 1, anytime that you're finding the limit of a constant, remember that that is just equal to the constant. So this is my answer, 1. Last one, we have the limit as theta approaches pi over 4 of secant theta minus tangent theta sine theta. Let's rewrite everything using only sine and cosine. Secant is 1 over cosine. Minus tangent is sine over cosine. And then times sine. So this looks a little messier than what we started, but look at what happens. We have 1 over cosine theta minus sine times sine, that's sine squared theta, also over cosine theta. Since both of these fractions are over cosine, we can write this as one fraction, where in the numerator would be 1 minus sine squared, and everything is over cosine. 1 minus sine squared, this is a Pythagorean identity. If I come back here to my identity so you can see, we solved for it here. 1 minus sine squared is equal to cosine squared. So what I can do is take this 1 minus cosine squared and replace that with cosine squared. And now that's over cosine. Now remember, cosine squared is the same thing as saying cosine theta squared. It means that there's 2 of them. Just to be clearer, this is like saying cosine theta times cosine theta all over cosine theta. So one of these cosines will cancel. And all we have left now is cosine theta. So this is my limit as theta is approaching pi over 4 of not this anymore, but of cosine theta. And if you plug in pi over 4, if you look at your unit circle, the coordinate for pi over 4 is square root of 2, comma, square root of 2. And cosine and sine here are both the same, so my answer would be square root of 2 over 2. Now let's have a look at some special cases of limits with trigonometric functions. Here we're going to find the limit of each of these graphs using as x is approaching 0. So this is the function sine of x over x. So if I want to find the limit as x is approaching 0, that would be 1. Over here, we have the sine of 4x over x. And I want to find the limit as x approaches 0, which is the 4. This is the function sine of 6x over negative 3x. If I want to find the limit as x approaches 0, it would be negative 2. For this function, we have 1 minus cosine of 4x all over negative x. So the limit as x approaches 0 is 0. Here we have 1 minus cosine 5x over 2x, and the limit as x approaches 0 is 0. Last one, 1 minus cosine x over x, the limit as x approaches 0 is 0. So these are what's called special limits, and these are their properties. These are the three most commonly used special limits when it comes to trigonometric functions. The limit as theta approaches 0 of sine of c theta over c theta is equal to 1. Now this is only valid, these are for all of these special limits, as long as theta or x is approaching 0. Has to approach 0. If it approaches any other value, we cannot use these special limits. For this one, we have 1 minus cosine of c theta over c theta, and that's always going to equal to 0. And finally, the limit as theta approaches 0 of tangent c theta over c theta is equal to 1. So not only can we only use these limits if theta is approaching 0, but with these particular limits, they also apply for all of their reciprocals. So for example, if you had theta over sine of theta, right, this is the reciprocal, or c theta over sine of c theta, that would equal to 1. If this was c theta over 1 minus cosine c theta, it would still equal to 0. And if this was the limit as theta approaches 0 of c theta over tangent of c theta, the answer would still be 1. Now, these special limits, they help us and make evaluating limits much faster. These limits here, these are the same ones that we saw here, right? That first one, sine of 4x over x, that was this one here. As long as it follows, whoops, I went back. As long as it follows this format, sine of x over x, or sine of c, in this case is 4, over x, what we do is we just take those numbers. We have 4, and this is a 1, and we would divide it. 4 divided by 1 is 4. And that's what we found for this limit here. See? 4. Now this one, as long as you have the format 1 minus cosine of something divided by something times x, this will always equal to 0. Again, as long as the limit has that x or theta is approaching 0. Here, this is the same format as this one. We're just going to take those numbers and divide them. 6 divided by negative 3 is negative 2. And again, if you look back here to that particular function, the sine of 6x over negative 3x, we saw that the limit approached negative 2. So those are a couple of little shortcuts that you can apply when you're evaluating for these limits. Now let's look at some questions putting all of this together. We have the limit as theta approaches 0 of 2 sine of 5 theta over 3 theta. This is my special limit. So I'm just going to apply the operations with my numbers, because this is the 2 and 5. These are being multiplied. So this is 2 times 5 over 3. So this gives me the limit 10 over 3. Now over here, we have 1 minus cosine theta plus 2 sine theta all over theta. And this is for as theta is approaching 0. So perhaps we can apply a special limit here. Everything is over theta. So what you can do here is split the fractions. But when you're splitting your fractions, you're not just splitting it any which way, you're splitting it so that you can apply these special limits. We know that 1 minus cosine theta over theta is a special limit. See, because all of this is being divided by theta. And then plus, right, because of this plus here, the 2 sine theta is also being divided by theta. So you see what I mean, that I split it up. Everything is over theta, everything is being divided by theta. So I split it up so I can see my special limits. 1 minus cosine theta over theta, this is 0. Plus 2 sine theta over theta, we know that sine of theta over theta is 1, so multiply the 2 is 2. And 0 plus 2 is equal to 2. Over here we have the limit of theta cotangent theta. Now think of your special limits. We only have special limits for sine, cosine, and tangent. I know that cotangent is 1 over tangent, so I can rewrite this as theta times 1 over tangent theta, which if we multiply that, that gives me theta over tangent theta. So this is my limit as theta approaches 0 of theta over tangent theta. If I go back a second to my special limits, remember that I said that the reciprocal also gives you the same thing. Theta over tangent theta is the reciprocal of tangent theta over theta. So this is going to equal to 1. Now, last one here, we have the limit as theta approaches 0 of sine theta minus sine theta cosine theta all over theta squared. Now, the first thing I notice in the numerator is that both of these terms have a sign in common. So I'm going to factor out a sign. And that would leave me with 1 minus cosine theta, and everything is over theta squared. Now I want to rewrite this so that I can apply my special limits. Theta squared is the same thing as saying theta times theta. So I can rewrite this denominator as theta times theta. Now these are my special limits. I can split up my fractions again here, except this time it's multiplication and not addition like here. So when I split this is the same thing as saying sine of theta over theta times 1 minus cosine theta over theta. Now remember, if you're unsure if this is the same thing as the original equation, if you multiply fractions, you're only multiplying numerator with numerator, denominator with denominator. Sine theta times 1 minus cosine theta gives me the numerator, and then theta times theta gives me the denominator. According to my special limits, this is equal to 1, and this is equal to 0. And 1 times 0 is 0. And that's limits of trigonometric functions.